I'm going to continue with this problem from exam 25, question 6. Earlier we answered part A for allele A, and we came up with an answer of 3/8. Now we can continue with this, and I'm going to continue with allele A. We had earlier started with the problem that tells us that all the males of generation 1 are heterozygous for dominant mutant allele A, and their descendants are to be determined. These two are wild type, not descendants. And the way we had pursued this, and I will rewrite this, is for people in the second generation, their father can produce 50% chance of wild type, 50% chance of mutant allele. Those are the gametes that he can produce. The mothers of generation 2 can only produce that, so we end up with the possibility of either wild type or equal probability of members of generation 2 being wild type or heterozygous, and I can combine that to say what kind of gametes they can produce, to say they will produce 3 wild type gametes for every mutant gamete at locus A. So I had earlier done that for looking at this individual here, and I had shown that both of her parents, then I'll put 1A, would do this, and we can continue that. So what I had done earlier was to show that in her case, her father produces that ratio of gametes, her mother produces this ratio of gametes, so there are 9 chances of wild type, 3 chances of heterozygous here, plus 3 chances of heterozygous here, and 1 chance of homozygous mutant. The first question asked about that. The next question here, B, asks about individual 4, 4. 1, 2, 3, 4. 1, 2, 3, 4. So asking about this individual. We have just determined in the previous part her, and we were concerned about her genotype. Now we want to continue. We want to know about the gametes you produce because we're interested in his genotype. So I'm going to show you something that's another way of looking at this. Just like I had before said, I can take this Punnett square and look at all of these together and generate the frequency of gametes that that individual can produce. What was that? That was 2, 5, and also 6 is the same. In this case, we were looking at, this was the chart for 3-4. I'll keep it labeled in case I need to go back to it. So the question is, what kind of gamete distribution does she produce? She can produce plus gametes or A gametes. So to do this, I want to know the ratio. So all I have to do is count. 9 plus 9 plus 3 plus 3. 9 plus 9 plus 3 plus 3 is 18, plus 6, that's 24. So for 24 chances of a wild type gamete, there are how many chances for a mutant gamete? 3 plus 3 plus 1 plus 1. So that's 6 plus 2, that's 8. So the ratio is this, and if you notice, if I divide by 8, I get this, and that's just what we started with, which is good to keep it simple here. Not surprising, you want to be careful, but in this case, all the members of generation were the same, so all the members of generation 2 are the same, and the frequency, the allele frequency, this is getting into population genetics of course, but the allele frequency hasn't changed, so we're not surprised that she and her brothers and her cousins or whomever, all of generation 3, have the same distribution of genotypes and the same relative production of gametes, except for these frozen embryos, these people who are derived from frozen embryo and are wild type. So if we want to determine individual 4-4, well, we know both of the parents are this, so both of the parents produce 3 to 1, 3 to 1. So he is actually the same as the previous problem, and the answer is the same. The answer will be the same. That has a single copy of allele A. Well, that's 3 plus 3, which is 6. 6 divided by a total of 9 plus 1 plus 3 plus 3 plus 6. So that's 6/16 or 3/8. And that's not surprising because nothing has changed between generations. The allele frequency is the change, and they both have the same. So I'm going to write here 3 plus 1a, 3 plus 1a, and I'm not surprised that he's the same as his mother and his father, who go all the way back up. Now the next case, which is a little more complicated, I'll continue in this video, 5-1. So 5-1 is a couple more generations down. We know that she is the same as her brother, so we just figured that out, right? So these are all the same. So what she will be is that, and we know that she will produce 3 pluses per 1a. We've already done that because 3-4 is the same as 3-5 is the same as all of the above. What's a little bit different is the father in this case, because we have the mother we know, but the father is different. The father produces only. So to determine 4-2, I would make another Punnett square in which I'll show the father produces only wild-type gametes and the mother produces 3 wild-type per 1 mutant, and that means we have 3 chances of homozygous wild-type to 1 chance of heterozygous. That's fine. We're not asked about his genotype, we're asked about, we need to know what kind of gametes he produces. So we do the same thing we did earlier and we count them all up. So there's 3 plus 3 plus 1, that's 7 chances of a plus gamete, and only 1 chance of an A. So I'm going to write here 7 plus 1A, and we'll do another final Punnett square for individual 5-1, where the father is 7 chances of a wild-type gamete, 1 chance of a mutant. The mother is 3 chances of a wild-type gamete per 1 chance of a mutant. And now we can do the Punnett square to see the possible genotypes and distribution of genotypes, and that will allow us to answer the question. So 7 times 3 is 21. So 21 chances homozygous wild type, 3 chances from here of heterozygous, 7 chances from here of heterozygous, and 1 chance of homozygous mutant. And the question is asking us single allele of A. So single allele of A means we want these two, and 7 plus 3 is 10. So that will be 10 divided by a total of 21 plus 7 is 28. 28, 29, 32. Not surprised by the number 32, as it's a product of 2 to the power of 5, or 21 plus 7 plus, that's 10, 10, 22. So it's clear. And we can reduce this 10/32 to 5/16. So the answer here is 5/16. I'll continue this problem in the next video.